Welcome to the physics class for January 21st. As usual, a couple announcements before we get started. Where did I write them all down? I wrote them, here's where I wrote them, okay. All right, first off, the test rework. Don't forget that it is a required assignment to redo all the problems that you got, well, actually redo all of the problems on the test, not just the ones you got wrong, but I want you to redo all of them. The exception is that those of you who got 100% or higher, because remember, it's actually possible to get more than 100% thanks to the extra credit problem. So when you look on Aspire, not Canvas, but Aspire, if Aspire tells you that you got 100% or higher, then I will automatically give you credit for the rework. You don't need to do any of them. But if you got anything less than 100, like if you got 99, then you got to redo all of them, including the extra credit problem. On the original test, the extra credit problem was extra credit, but now it's a required problem. I want everybody to know how to do that. And the deadline for that is Saturday at midnight. Now, if you miss the deadline, it's not the end of the world, but it'll cost you a late pass if you get it in after Saturday at midnight. So if you want to avoid a late pass, get it in before then. Tutoring sessions, don't forget about those. Tuesdays, Thursdays, Fridays, Saturday, we get lots of tutoring sessions. So you should get lots of opportunity to get help. If for some reason the tutors are not able to help you out, then contact me. Now, Mr. Wilson has declared that Friday mornings from 9 until 10:30 is supposed to be the office hours where teachers are available to talk to students. But then he went and assigned me to teach the U of U physics class, which meets Fridays from 9 until 10:30. So that's kind of a problem. So all I can say is if the tutors are not able to answer your questions, send me an email. If I am not able to adequately answer your question via email, I will set up a one-on-one Zoom session in whatever time we can both meet at. And I'll just one-on-one, just me and you. So we will solve your problems, but try the tutors first, please. And I see somebody just typed something in here. Oh, okay, it was Sam saying perish, huh? If tutors can't answer your questions, then just perish. Yeah. Okay, so let's talk about last night's homework. Here are the answers in just a second. Okay, so here are the answers, the ones that you haven't already looked up, at least 1 through 8. Problems 9 through 13, those are ones that I'd like to discuss, at least some of them. So let's do what we normally do. Let's have you vote if you could only see one problem worked through. And let's just restrict it just to problems 1 through 8 for right now. Of those problems 1 through 8, if you could only see one problem worked through, what would you like it to be? And hopefully we'll be able to get more than one, but let's try just one. All right, I'm seeing some votes for problem 4. I'm seeing some votes for problem 8. Looks like it's pretty well split evenly between problems 4 and 8. Yeah. Okay, well, let's do both. I think we'll have enough time. All right, let's start with problem number 4. And where's my glasses? Okay. All right, that was the spring problem, if I remember right. Okay, so they tell us the K value of the spring, the spring constant. They tell us that K is 144. Notice the units on it. It's newtons per meter. And then they tell us how much the thing is compressed. So delta X is 16.5, but notice the units on it. That's centimeters. Do you see a problem? Yeah, those of you who got the wrong answer, this could very well be it. We got centimeters here, meters here. We've got a unit mismatch. That's not going to work. So we got to get the units to agree. And the best way is let's use standard physics units. Okay, so if we rewrite that in standard physics units, then delta X is going to be 0.165 meters. So if we stick that into the equation, then we should be good. And which equation do we stick it into? Well, we talked about this last time, and the book did a good job, I think, of explaining it. So if you have a spring and you compress or extend that spring, the amount of energy in the spring is equal to however much work you did when you compressed it. So you know that work equals force times the compression distance. But if the force is not constant, what do? Well, you put an integral in front of there. And you say, well, wait a minute, that's calculus. I don't know calculus. You don't need to know calculus, okay? If you do force versus position, and then you find the area under the curve, remember we did that before, and it works out to be 1/2 kx squared. That's the work that we do to compress the spring. Therefore, that's how much energy is stored in the spring. So as long as you use this number for delta x and this number for k, you should get, oops, wrong one, not that one. Sorry, my eraser didn't want to. Why is my eraser not erasing? Okay, there we go. Okay, so you should get 1.96 joules as long as you do that. So if you got the wrong answer, I'm willing to bet it's because of dimension mismatch. Okay. It's trying to stage a rebellion. Yeah. Okay, now problem number 8. Which one was that? Oh, that's the pendulum on another planet, right? Okay, that's a good one. I like that one. Okay, so we've got a pendulum and, or actually, here's this, we're on some other planet and we want to measure the value of G. So one way we could do it, here, let me just stop sharing for a sec. One way we could measure G is we could just pick up some object, drop it, try to measure the acceleration, and bingo, we've got G. But you know, it's actually more accurate if you use this pendulum trick, which is pretty cool, because we now know the relationship between the period of a pendulum and the length of the pendulum and the gravity, the acceleration due to gravity. So now we haven't derived this yet, and I promise you we will, but not today. But the book claims that the period of a pendulum is 2 pi times the square root of L over G. Now we did some experiments where we measured the period of a pendulum, and the data that we got corresponded with this equation, which some people might say, well, we proved that the equation is correct. No, we didn't prove it correct, but we did gather evidence which lends us to believe that maybe it might be correct because our data matched this prediction. So not today, but next week, we will derive this. But for right now, we'll just go ahead and trust that it works. Okay, so in problem number 8, they tell us what the period of the pendulum is. They tell us what the length of the string is. And so our job then is to figure out what G is, because we know we're not on the Earth, we're on some other planet. So it's not really a physics problem, guys. It's just a math problem, and you're good at math, right? So if we want to solve for G, first thing I'd recommend we do is let's square both sides. So we get t squared equals 4 times pi squared. And when we square root the right side, that square root goes away. So then we're going to get L over G. And so then let's just take the G and the t squared and swap places with them. So that's going to give us G equals 4 times pi squared times L divided by t squared. And so now it's just plug and chug. Take the numbers that they gave you, plug them in there, and if you do it right, you will get 9.1 meters per second. Now, it might be a dimension mismatch, but I don't think so. I think, okay, they gave us the length in meters. They gave us the time in seconds. So yeah, those are all standard physics units. So we don't even need to worry about dimension mismatch there. So I think we're good on that problem too, right? Does that answer your guys' questions? If you don't say no, I'm going to assume the answer is yes. Okay. All right, now problems 9 through 13. I don't have time to talk about all of them, but let's just talk about a few of them. Problem number 9 says Hooke's law. It says we got two springs and they look identical, but we want to know which one has the greater spring constant. Okay, well, let's take two springs that do not look identical. Okay, so here's one that's got the big thick wire. Here's one that's got the little thin wire. And so if I squeeze this one, well, it's not easy. This one's really stiff. And this one here, yeah, this is pretty easy. I can squeeze this one. But this guy, I can't. So this one has the greater spring constant. He's the one that's stiffer. So if I had two identical springs, or at least ones that looked identical, okay, if I want to know which one has the greater spring constant, just try to squeeze it. And whichever one is stiffer, that's the one with the greater spring constant. And problem number 10, okay, so it says we're gonna take a rubber band, and I don't have a rubber band, so I'll just take a spring. Okay, so if I were to hang a bunch of objects on this spring, so I start off with something that doesn't have a lot of mass, and then I switch to one that has more mass. Okay, so the spring is going to get stretched and stretched and stretched. Okay, so the question says, how can you tell? Well, so we're going to make a graph here of the stretch distance as a function of the force. Okay, so let's do that. All right, so let's say that we're, actually, it doesn't matter whether we do, which one is our independent variable. So we can do force as a function of stretch distance, or if we want, we could do stretch distance as a function of force. We could do it either way. So if we do it the first way, we're going to get a slope that looks like that. If we do it the second way, we're going to get a slope that looks like that. But at some point, it's going to go nonlinear. And that is the point where Hooke's law stops applying. That's the point where we have now deformed the spring or the rubber band or whatever, so that if we go past this point, when we let go of the spring, it is not going to go back to its original shape because we have deformed it. So Hooke's law only applies in this region here where it is linear. So the answer to the question is, how do you know whether it obeys Hooke's law? Well, if it's linear, it obeys Hooke's law. If it's not linear, then we've exceeded the Hooke's law region. And there's a couple others in there as well, but I don't want to take the time to do them. We got a lot of important stuff we have to do today. So as usual, if you have questions about last night's homework that we weren't able to discuss just now, stick around at the end of the class and we'll talk about it then. Let's go into the new material for today. Okay. Okay. All right. So we're still working in chapter 14 today. Let's skip down to here. Okay. So now today is the day where we're going to make the connection between pendulums and masses on springs and waves. So let me blow this up a little bit here. So, okay. So what you see right here is something that I actually have in my classroom. I didn't bring it home here, but it's a special machine that's got a little thing sticking out of it. And what you do is you take a string and you tie a string on one end. And then this thing is connected up to a motor. So it's going to go up and down and up and down and up and down. And so what it's going to do on the string is it's going to send a whole bunch of pulses. So every time it goes up, it sends a pulse down the string. And then so if you go to here, all right, so this shows where the blade is at the highest point, and it has pulled the end of the string up. And then when the blade goes down a little bit, so it pulls the end of the string down, goes down a little bit more, pulls the end of it down all the way down the bottom, and now it comes back up again, and then it repeats. And so what's happening here is that we've got all these pulses, and let me turn on annotation here so I can, okay. So this is a pulse. And when the thing comes down to the middle point here, this pulse has moved over to here. In fact, tell you what, let me zoom back. Oops, I got to turn off annotation before I touch my screen. Okay. In fact, tell you what, let's just come down here. All right. So what happens here is we've started a pulse right here. When the wand comes down to here, the pulse has moved over to here. Now the one is down here, the pulse has moved over here. Wand comes back up here, the pulse moved over to here. So this pulse is moving down the string. That doesn't mean that the string is moving that direction. If you were to look at the string, if I were to like tie a knot on the string right here, what I'd find is that that's going up and down and up and down. That knot does not move in the X direction. That knot only moves in the Y direction. But the pulse on the string, the deformation of the string, that pulse moves. So it starts out here and then it goes here and then goes here and then goes here. So we're sending a whole bunch of repeated pulses down the string. And if the blade is undergoing what we call simple harmonic motion, which is exactly the same motion that a mass on a spring undergoes. Okay, so here's the mass on a spring. So I pull it down and then I let it go. And so it goes like this. So this type of motion is called simple harmonic motion. It's going up and down and up and down. And if we were to graph the height of the mass as a function of time, we would get a nice sinusoidal shape. So a sine wave, or you guys know that a cosine wave and a sine wave are the same shape, they're just shifted, right? So that shape, we call it a sinusoidal shape, right? So if the thing that is generating the wave is undergoing sinusoidal motion, up, down, up, down, up, down, then the string is going to end up being shaped like the sine wave. And so this is not really a string. This is actually a wire, but I'm gonna use it. Okay, so if we were to take a photograph of the string and freeze time, this is what it would look like. Okay, and then as time goes on, it would move along, but it's not really the string moving. It's just the pulse in the string that's moving. Okay. All right. Now, there are other kinds of waves that at first glance might look like they're different, but mathematically, they are the same. So for instance, let's suppose we take a slinky. You guys have all played with slinkies, right? Okay. So let's take a slinky and let me turn on annotation so I can draw a little better. So what we're going to do is we're going to use our finger and we're going to bunch up the coils here so that we force these coils here to be very tightly packed. And the rest of the coils are loosely packed. Okay. But then when we lift our finger up to let it go, what happens is all of the tightly packed coils here, they want to expand. And so the coils that are over here, they end up getting tightly packed. And so here, so this is where this pulse has moved from here to here. Okay, but these guys, they don't like staying tightly coiled. They want to push away, so they're going to push away, and so they're going to compress these guys, and so now these guys are compressed, and then they go and so forth and so on. So what we're going to have is we're going to have a pulse that's the exact same kind of pulse that we had right here. It doesn't look the same, but mathematically, it is the same. So if we were to make a graph of the tightness of the coils as a function of distance, okay, and also let's assume that we don't just do one pulse, because this vibrating blade up here, it's not just going up and down one time. It's going up and down and up and down and up and down repeatedly. So we're going to assume that the finger here is doing the same thing. It's going to create a tightly packed pulse, and it's going to send it out there, and then it's going to do it again and send another one. So what's going to happen is we're actually going to have we're going to have regions here where we've got tightly packed and then loosely packed, and then we have tightly packed and loosely packed and tightly packed. So if we were to make a graph of the tightness of how the coils are packed together as a function of distance along the slinky, we would find that it would look like this. Okay, this is where they're tightly packed. This is where they're loosely packed. This is where they're tightly packed again. And so mathematically, this wave and this wave are exactly the same. The only thing is what's on our y-axis. For the slinky, the y-axis is how tightly the coils are packed. If it's a string, then the y-axis is how far the string is up above or below the equilibrium point. Okay, so these are two waves that look very different, but mathematically they're identical. And there are names for these that you need to know. So if we have the kind of wave that most people think of when they hear the word wave, where the string is going up and down and up again and down again. So the wave pulse is moving left to right. But if you were to look at the string itself, like if you were to tie a knot in the string, okay, and so here's a knot that's tied in the string, and you watch what happens to that knot, you'll find it does not move left to right. It moves up and down and up and down and up and down. So the wave pulse is going horizontal, the string is going vertical. That is what we call a transverse wave. Okay. Now it doesn't have to be horizontal vertical. I mean, what we could do is we could make the wave go up and down. I could take my string, okay, I could take my string and I could wiggle it like this. So in that case, the pulse is going upwards and the string is vibrating horizontally. So don't think of it in terms of horizontal and vertical. The best way to think of it is the wave pulse is, oops, I keep forgetting to turn on annotation. The wave pulse is moving this way, and then the knot in the string is vibrating in a direction that's perpendicular. That's the thing to look for. So if the vibration of the knot is perpendicular to the direction that the pulse is going, that's what we call a transverse wave. Now with the slinky here, so I don't want to really tie a knot in my slinky. That's going to ruin my slinky. So what I'll do is I'll take a little piece of tape. And so I'm going to put a piece of tape right here. And then I'm going to have all these pulses go past here. And if you watch the tape, you'll see that the tape is pulsating, it's vibrating in a direction that is parallel to the direction that the pulse is going. So in this case, the pulse is going left to right. And if you look at the tape is going right for a little while and then left for a little while and then right for a little while and then left for a little while. It's parallel. So if that happens, that would be a longitudinal wave. Okay. Now you might think, well, okay, great, but how often do you really care about a wave in a slinky? Well, what about sound? A sound wave is very much like that slinky. So if I sit here and I sing to you, if I go, what you're experiencing is a longitudinal wave. It's a slinky type wave. What's happening is my vocal cords are going forward and backward and forward and backward, and they're pushing the air. And then they come back and then they push the air a second time and they come back and they push the air a second time or a third time. Exactly the same as this slinky is working. So this would be, I keep forgetting when I stop sharing, I have to go back and return on the annotation. So the finger right here is acting like my vocal cords. So it goes forward for a while, which sends off a pulse. And then it comes back and then it goes forward again, which sends off another pulse. Every time that finger goes forward, it sends off a pulse. That's exactly what's happening with my vocal cords or the speaker that you're listening to. You know, if you're listening to music, you got a recoil speaker. That's what's happening is there's the drum inside the speaker that's going forward and backward and forward and back. And it's causing areas of high air pressure that are separated by low pressure. So let's say I've got a whole bunch of pulses. So here's one pulse, here's the other pulse, here's another pulse. Okay, so we have all these regions of high air pressure, and they are all separated by a region of low air pressure. So if I were to plot pressure as a function of distance, I would find it would look like this. So it'd be a really nice sine wave or cosine wave, depending on which you want. You know, remember, cosine waves and sine waves are the exact same shape. They're just shifted left and right is the only difference between them. Right? So there are, in fact, lots of examples of longitudinal waves in nature around you. And there are also lots of examples of transverse waves. Okay, so let's take a quick poll here. What about if you go out and you look at the ocean and you look at the waves on the ocean? I want you guys to type into the chat box, what do you think those are? And type it in a private message, please. Do you think the waves in the ocean, are those transverse or are those longitudinal? Let's see everybody type into the chat box. Come on. Okay, all right, I'm starting to see a few now. Okay, keep going. I want to see more. Okay. All right, what I'm seeing is about half and half. Okay, well, I was hoping that somebody would recognize that this is actually a trick question. You guys know me well enough by now. You should know that that's the way I do things, okay? If you were to actually examine it, the best way to do it would be put a cork in the water and watch the motion of that cork as waves go by. And so what you'll find is that the cork, whoops, I keep forgetting. One of these days I'm going to remember. Okay, there we go. Okay, so let's say here's the cork. And right now it's at the highest point. Okay, well, as the wave passes, that cork is going to move forward a little bit. And as the wave falls, it's going to move down. And then as the next one comes, it's going to move this way. So that cork is actually going to go through a circular path. So it's actually a combination of both longitudinal and transverse. Okay, so motion of water waves is actually much more complex than most people realize. If you just look at it, I mean, if you just look at the picture here, you say, wow, that looks like a nice transverse wave. But if you look at the motion of the cork, you'll see it's actually doing this complex thing. It's actually a combination of both transverse and longitudinal. Okay. Now, in your homework tonight, well, they're going to ask you a couple. They're going to give you a couple of examples of various types of waves, and they're going to say, is this transverse or longitudinal, or is it like water where it's a little bit tricky? But they're also going to ask you to do some calculations. So you're going to need to know some terminology. What I'm about to go through is something that I hope is review for all of you. In your math class, you should have talked about waves by now. Some of you, depending on what math class you're in, maybe you might not have gotten to this point yet, but you will really soon. Okay, so let's learn some language here. If you have a wave, now I'm gonna do all this assuming that these are transverse waves, but you know, longitudinal works the same way. If it's a longitudinal wave, then instead of measuring displacement as a function of time, I would measure something like pressure as a function of time, and I'll still get a wave that looks like this. So it still works. Okay, so wherever you have a place where the wave is at the very highest point there, okay, we call that the crest of the wave. Wherever the wave is at the lowest point, we call that the trough of the wave. The height of the wave is called the amplitude, but be careful, because one thing that I've seen a lot of students do is they think that the amplitude is the distance from the lowest point to the highest point. They think that's the amplitude. That is not the case. The amplitude is measured from the center point to the highest. So this distance is the amplitude. Now it turns out that that distance is going to be the same as this one. So as long as you just take the absolute value and don't worry about whether it's above or below, either one of these distances would be the amplitude. Okay, so remember, it is not trough to crest. It's midpoint to crest. Don't make that mistake. All right, let's take another test here. You see this down here where I put a question mark there? Okay, so based on your knowledge from your math class, I want you to tell me, what is that distance? Give me a word that corresponds to that distance. All right. And I see that most of you are sending your message in privately, a few of you sending it publicly. Okay, well, don't worry, it's not the end of the world. Okay, all right, now most of you are saying that that distance is the wavelength. But some of you are saying no. Some of you are saying it's the period. So that's the question. Is this distance equal to the wavelength? Or is this equal to the period? Or is it both? Well, okay, it's not both, okay? But it could be either. It could be one or the other. Before you can answer which one it is, you need to know what is the independent variable in this experiment. You'll notice that the dependent variable is labeled, but they did not tell you what is the independent variable. And there's two things that the independent variable might possibly be. The independent variable might possibly be distance from the edge of the string, or the independent variable might be time. So how does this work? Okay, so well, let's suppose I've got my string here, and so I start shaking it, okay? And then I take a photograph of it. All right, so let's say that this is what it looks like. Okay, so when I take a photograph of my string, so I'm here sitting here shaking it like crazy, I take a photograph and I freeze time. So this is what I get, right? So now, what if I were to graph this, if I were to put this on a graph, this would be the starting point. And as I move over here to your right, okay, what I'm seeing is this is the distance from the edge of the string. So if I were to graph this, my independent variable would be the distance. Okay, so if that's the case, if my independent variable is the distance, then the distance from this crest to that crest, that would in fact be the wavelength. But that's not the only way that I could do it. What I could do is I could take my string and I could tie a knot in the string here. So pretend there's a knot right here, okay? And so now what I do is I shake it so it gets going, you know, like you saw before. But this time I'm not going to take a photograph. I'm not going to freeze time. What I'm going to do is I'm just going to look at this one point where the knot is. Okay, so let me go ahead and actually tie a knot. Easier said than done. When you want to do it in a hurry, it's easier said than done. Okay, so let's just pretend that there's a knot right there. Now, okay, if I make it a little bigger. Okay, so here's my knot. We don't need to pretend anymore. We actually got a knot. Okay, so what I'm going to do now is I'm going to shake this thing so it's going to go up and down, but I don't care about the rest of the rope. All I care about is the knot. And what I'm going to do is I'm going to track the position of the knot as a function of time. And what I'll find is that it goes up and it goes down and it goes up and it goes down. So if I were to graph the position of the knot as a function of time, I would get something that would look like a sine wave. Okay, so this is the position of the knot, or this is the displacement of the knot from the equilibrium point as a function of time. Okay, so I would get something that looks like this. But if I were to do the displacement of the rope, not just the knot, but now the entire rope, as a function of distance, so what I'm doing here is time is frozen, okay? Then I get something that looks like this. And so in this case, this distance would be the wavelength. which, by the way, do you guys know that this symbol right here, this is the Greek letter lambda. Actually, I think there's a B in there. Oops. Okay, so it's the Greek letter lambda. It is the wavelength. Okay, but if, on the other hand, I'm doing this graph here where my independent variable is the time, okay, then it is not the wavelength. Then it's the period. And notice, lowercase t means just any old time. Uppercase t means one very special time. It means the period. Okay. All right. So if I were to give you a test where I give you a question like you see right here, if I were to say on the test, what does this distance represent? If I haven't told you what the independent variable is, then you can't answer the question. So the correct response would be to say, hey, Mr. Hendricks, if you don't tell us what the independent variable is, we can't answer it. So tell us, what's the independent variable? Okay. All right. So there will be a couple of questions where they will ask you, make sure you understand the different terminologies here. All right. Well, not just that. We also have a couple other things. You're going to have to look at waves that are moving, and you're going to have to look at the wavelength and the speed and the frequency, and you're going to have to see how they are all mathematically related. So there's a very important equation that you're going to be using in tonight's homework and for the rest of the year. In fact, this equation is so important that I think we better take a little time to derive it. I would recommend that you guys turn to a new page in your notebook. And up at the top of the page, I want you to write derivation of super important wave equation. Okay. Now, it is so important. It really should have a name. You know, it should have a name like Hooke's law or Watt's law or whatever. But as far as I know, it doesn't really have a name, which is really a shame. Maybe we call it Hendrix's equation. But there is a relationship between the speed of a wave and the frequency of the wave and the wavelength and all those things. And you need to know it because it is going to be the equation that you are going to use more than any other equation from now through the end of the school year. So get ready to derive it. And let me get a whiteboard out here. Okay, so let me just first tell you what we're going to do. We're going to take a string and we're going to vibrate it at a certain frequency. So remember, frequency is how many vibrations per second. Okay, so the thing that's causing the wave to go is going to be vibrating with a certain frequency. And so what's going to happen is I'm going to have waves going out, where if I were to take a photograph of them, they would look like this. Okay, and so depending on the frequency and depending on how fast the wave moves, that is going to determine what the wavelength is. And so how are they all mathematically related? Okay, well, let's draw a picture. And so in black ink, I'm going to draw a picture of what it looks like when t equals 0. All right, so, and my independent variable here is going to be the distance from the end of the string. My dependent variable is going to be the displacement relative to the equilibrium point. And let's say at t equals 0 looks like this. Okay, and now I'm going to switch to red ink. And so t equals a small number. Okay, and so what has happened is that, let's say that whatever is the paddle here that's going up and down, okay, so it's moved down to here. And so what has happened is that the wave will have moved. And okay, so if we were to look at the wave, we would see that the crest that used to be here has now moved over to here. And this crest that used to be here has now moved over to here. So this wave is moving. Now remember the string, which is the thing that's actually, physically the thing that we're moving up and down. The string does not move from left to right. The string moves up and down, but the crest is moving, and the crest is moving right there with some speed. Let's say it's moving with the speed v. Okay, now I'm going to switch to blue ink, and let's say that the t now, the time has now equaled the period. Okay, so what that means is that this wave has now moved over so much that if I were to graph it right now, we would find that it now lines. So this crest, the crest that started out up here, has now moved one full wavelength. So this crest now lines up with where the adjacent crest used to be. So the distance that the crest has moved is one wavelength, and the crest is moving at speed v. Okay, and the time that it took to go from there to there is the period. Okay, so this picture is the most important part of the derivation. Make sure that this picture is in your derivation. All right, the mathematics is actually astoundingly easy. Whenever you have something moving at constant speed, we can get away with using everybody's favorite equation, dirt. Distance equals rate times time. Okay. Now, if it's accelerating, then we have to use the Dr. Seuss equations. But if it's moving at constant speed, we can just use distance equals rate times time. So if the thing has moved a distance that is exactly equal to lambda, so d then is lambda, and it's moving at speed v, so r is v, and the amount of time that it took to move that distance is the period. So distance equals rate times time becomes lambda equals the velocity times the period. Okay. Now in the book, they're going to say, well, but we want to know what the frequency is, not the period. So hopefully you guys remember we talked about last time, frequency is the inverse of the period. Or if you prefer, period equals the inverse of the frequency. They both mean the same thing. Remember that frequency is defined as how many times per second something happens. Period is defined as how many seconds per time. They are inverses of each other. So wherever I see a t, I can replace it with 1 over f. So I can just take that t, replace it with 1 over f, and what I'll get is lambda equals v over f. And there you go. That is it. We are finished. That was the easiest derivation we've done all year, but probably one of the most important, because I'm not kidding when I tell you that you are going to be using this equation for the rest of the year more than any other equation. So lambda equals v over f. So whenever you have something that is causing a wave to happen, so like, okay, for instance, let me go back to this guy right here, and let's zoom in on here. All right, so this paddle that you see, this blade that you see right here, this guy is going up and down and up and down and up and down a certain number of times per second. So that is the frequency, right? And so this pulse is going to move down the string here. Now, the speed of the pulse, so the velocity is determined, okay, by the properties of the string. This is important. Velocity is not a function of the frequency. So, and here, this is kind of a shame. I have some great equipment set up in my lab, but you're just going to have to kind of watch. All right, so if I take a string and I'm going to pluck it, and I see how fast does that pulse move down the string there. Okay, so if I were to do that, And if we were in the lab, I could actually do it for real. What you'll find is that that pulse moves at a certain speed, and it doesn't matter how frequently I go. If my hand is going like this really fast, or if my hand is going relatively slow, the speed that each one of those pulses travels down the string doesn't depend on the frequency that I'm vibrating it at. The only thing that it depends on is properties of the string. So if this is a light string, it's going to go at one speed. If it's a heavy string, a heavy rope, it's going to go at a different speed. Also, it depends on how tightly the string is stretched. If the string is stretched really tightly, that pulse is going to move really fast. If the string is only stretched a little bit, then the pulse is not going to go quite as fast. So the speed of the wave depends only on the properties of the string. It is not dependent on the frequency that the thing is moving at. Okay, so what we find is these pulses are going to, let me hang on a second. Okay, so these pulses are going to be moving at some speed v that, as we just said, is a dependent on the string. Okay, and so we've just determined that the frequency is equal to the wave velocity divided divided by, oops, sorry, got that wrong. Try that again. The distance. Okay, so d equals RT. So distance is wavelength, r is velocity, and then we get 1 over f. Okay, so if I were to tell you that the frequency that I'm doing it at, let's say that it's 4 hertz. So your first question would be hertz. What's a hertz? Well, hertz is the unit that we use to measure frequency. Hertz means how many times per second. So if I say the frequency is 4 hertz, what that means is I get 4 vibrations per second. That's what 4 hertz means. Okay, so the frequency is 4. And let's say that we measure the wavelength. Let me clear some space here. So we do an experiment and we set up the frequency. So this thing is vibrating at 4 hertz, and we measure the wavelength, and we find out that the wavelength is 0.6 meters. So what then is the wave speed? Well, just use this equation, just rearrange it. So let's clear this out. Well, I don't want to clear the whole thing. Okay. So if we just take this equation, rearrange it, so multiply both sides by f, so what we get is v equals f times lambda. Well, f is 4, lambda is 0.6, multiply that out, and we'll get v equals 2.4, whatever units are the appropriate units. And so as long as we're using standard physics units, which is hertz for frequency and meters for distance, then everything will come out in standard physics units. So for the standard physics units for velocity are meters per second. Okay. So hopefully you guys see this equation right here, lambda equals v over f. That equation is going to answer most of your homework problems tonight. But also you might want to remember that the f equals 1 over t. You might find out that that relationship is going to come in really handy tonight too. Okay, so as long as you know this, I think that you'll be in good shape. Okay, any questions about that? Now, we are not yet done, not by a long shot. But before I move into some new stuff, I want to just see, are there any questions about what we've just done? Okay, not seeing any, not hearing any. Okay, all right, now, what I'm about to do is going to be review for many of you who are in the more advanced math classes. But for some of you who are still in Math 2 or Math 2 Honors, what I'm about to do might be new for you. You might not have reached this point yet in your math class, but you will soon. So here's the goal. What I'm going to do is I'm going to take this, this mass and this spring, and I'm going to put them on here. So I'm hanging it from the ceiling. I'm going to pull it down and I'm going to let it go. Okay, so it's vibrating and up there, up and down and up and down. I want to come up with a mathematical equation that will tell me what is the height of this thing above the tabletop as a function of time. Okay. Well, hopefully you guys know if it's going up and down and up and down and up and down, that's the sinusoidal shape that we've seen. So that is either going to be a sine function or a cosine function, which hopefully you guys know is really the same thing. Okay, so let's write a couple things down. So get out your notebooks and write it down. So what I'm going to do is I'm going to do this little experiment. Okay, so I'm going to start. So right now it's at the equilibrium position. And let's say that the equilibrium position here is 1 meter above the floor. Let's do it relative to the floor. So that way, that's about a meter. Okay, so that's my equilibrium position. So when I start the thing going, it goes up and down and up and down. Okay, so when it's at the highest point there, let's say that at the highest point, it's 1.1 meters above the floor. When it reaches the lowest point, it's 0.9 meters above the floor. Okay, and then the other thing we want to measure is what is the period that it takes. How much time does it take to go up and down and up and down? Okay, so let's see. So about a half a second, maybe. Does that sound reasonable? Let's try that again. Yeah, if just eyeballing it. Okay, so let's write all this stuff down. And in fact, where I want to write it, come on, why is it not cooperating? Okay, here we go. Okay, whoops. All right, so I'm going to go into Desmos here. And because we're going to be using Desmos for this, but let's down here in the lower left here, let's write down all the stuff that we just figured out. Okay, so here's the floor and here's the mass. And so the equilibrium position is 1.0 meters above the floor. And when it goes up to the highest point that it ever gets, okay, then that's 1.1. And when it goes down to the lowest point that it ever gets, that's at 0.9. Okay, and we figure that the period is 0.5 seconds. All right, so I want an equation that is going to tell me what is y as a function of time. Now, Desmos prefers everything to be as a function of x. So I'll go ahead and I'll put it in x, but wherever I put x, you need to know that that's really time. That's really not x. Okay, so it's going up and down and up and down. So you guys are going to say, well, that's either a sine function or a cosine function. Okay, well, let's go ahead and put it in here. Let's go with sine for now. Let's say that we think that y equals the sine of t is what I really want, but Desmos is going to force me to call it x, and I can deal with that. Okay, so there you go. Y equals the sine of x. So I like the shape of the graph, but it's centered on y equals 0. So you see, let me turn on the annotation again. Okay, so you see that the equilibrium point is 0. So the highest it ever gets here is 1. The lowest it ever gets is -1. And that's not what I want. Okay, so that's not too good. So I need to deal with that. What would you guys recommend I do? So I need to move this guy up. So how about let's do this. Let's just come in here and let's just say +1. Okay, good. It got moved up. So now the oops, I keep forgetting here. Okay, so now my equilibrium position is in fact 1 meter above the ground, but it's going too high and too low. My amplitude is wrong. So the default amplitude in Desmos is that the amplitude is 1, and that's not what I want. I want my amplitude to be 0.1. So anybody got any suggestions on what I can do? How can I make the amplitude be 0.1? Come on, somebody speak up. How do I make the amplitude be 0.1? Hello, is anybody there? I know that some of you guys know this. Ah, okay, good. Okay. All right, thank you. Had me worried. Okay. So Dylan is suggesting that what I should do is I should go in front of the sign there, and I should put a number there, and the number that I put there is whatever I want the amplitude to be. So in this case, my amplitude is 0.1, so I'm going to put in 0.1, and there you go. Now it's hard to see because I've got too much writing there. Let's clear out most of that writing. So come on. Why is my eraser not one? Okay, there we go. So let's get rid of all this. Okay. All right, it's looking pretty good. Let me expand this out a little bit here so that I can see a little bit more clearly. Okay, so hey, it's looking pretty good. So you see that we've got, so the equilibrium position is in fact 1 meter above the ground, which is what we wanted. So that's good. The highest it ever gets is 1.1 meters. Yep, okay. Lowest it ever gets is 0.9 meters. Okay, good. I'm liking what we're seeing. Ooh, except for what about the period? Okay, so remember now that the x-axis here is really time. Okay, so this is time down here. So if I want to look at the period, well, let's see, let me move this over just a little bit here. Okay, so if I look at the period here, I'm thinking something's not right. So let's take this crest right here, and this crest right here. This is a number a little bit less than 2. This is kind of close to 8. So it looks to me like our period here is a little bit more than 6. It's about 6 point something. And that's not what we wanted. We wanted the period to be 0.5. What can we do to make the period be 0.5? Suggestions, anybody? No suggestions? Come on, I know that some of you guys have seen this. Think back to your math class. How did your math teacher have you do it? So the generic form here that we want is y equals a times the sine. Oops, that's supposed to be a sine, not a sim. Okay, a times the sine of t. Why do you suppose I left a space in between there? What is it that goes in between there? How about the letter B? Okay, so whatever we put in for A, that is the amplitude. B is the number that controls the period. Now, you might think that if we want the period to be 0.5, then we should just go ahead and put in 0.5. I mean, if A is the amplitude, a lot of people think, well, that means that B should be the period. So let's try that and see if it works. Let's put in a 0.5 here. So 0.5. Whoops, that didn't work. That didn't give us the answer that we wanted. So it did change the period. So B does in fact control the period, but B is not equal to the period. Okay, so I want some of you guys to tell me, what do we do? What is the relationship between B and the period? Come on, guys. I know that several of you are in Math 3 honors. And I know that you've covered this in your Math 3 honors class. And I know that some of you are in calculus, so you absolutely know this. You need a little help? Okay, I'll give you a little bit of help. In fact, I'll just go ahead and tell you because we're running low on time here. And now for some of you, if you're in the Math 2 class, then you haven't seen this. You probably haven't seen this yet. So for you, it's new. But for the rest of you, this should not be new. Okay, so B, oops, I keep forgetting to turn on annotation before I do this. Let me go back. Okay, so in fact, tell you what, let's just clean everything out here. Okay, so the way it works is if you got y equals a times the sine of b times t, okay? A is the amplitude. B is the number that controls the period, but B is not equal to the period. What happens is B equals 2 pi divided by the period. That is what we want, okay? So if we want the period to be 0.5, then the B value that we want to use is 2 times pi divided by 0.5, okay, which is 4 pi. But what is that? So 2 times pi divided by 0.5. So I get 12.6. So the B value that we want is 12.6. Okay, so let's see if that works. Let's type that in here. So instead of 0.5, let's type in 12.6. And okay, wow, boy, that certainly changed the period a lot. So let's zoom in a bit here and see if that is, oops, I keep forgetting, got to turn off annotation. No, I turned it off. Why isn't it going off? Okay, there we go. Okay, so let's see if we can zoom in a bit there. Okay, so it looks to me like we've done what we want to do. So here's one crest, here's another crest, from there to there is 0.5. Yes, we've got it right. So our equation now is exactly what we want. The midpoint of our oscillations is in fact 1 meter above the ground. The highest point is in fact 1.1 meters. The lowest point is in fact 0.9. So the amplitude there is 1 and the period is 0.5. So yes, this equation right here models what we want. Okay. Any questions about what I just did there? Okay, so I see somebody just sent me a private message. Oh, okay, yeah. So does it involve 2 pi? So yes, good for you. So I didn't see the message earlier. So when I was asking what's the relationship between B and 2 pi, so Miriam got it. She typed it in the chat box. I just didn't see it. Yes, so B is 2 pi divided by the period. So make sure that you guys write that down. Okay. Make sure that you write down. So if you want to do y equals a times the sine of bt, where that's all in parentheses, that b value is 2 pi divided by the period. Now this also works with cosines. Y equals a times the cosine of bt. Okay, that relationship still applies. In fact, let's go and let's play with that for a second here. Let's go in here. Let's see what this would look like if instead of sine, we had used cosine. In fact, tell you what, let's do. Let's just look at the generic, what I like to call the mother function. Let's just play with sines and cosines without any amplitudes or anything. Let's just go in here and let's say y equals the sine of x, okay? And so there's that. And then let's look at the cosine. Let's do y equals the cosine of x. Okay. You see the difference there? It's the same graph, is just shifted. So the sine function starts off at 0 and heads upwards. That's the sine function. The cosine function starts off at 1 and heads downwards. That's the cosine function. Now, there is one other very important detail that I purposely neglected because I was worried that we might run out of time, but I see that we have a little bit of time left. So let's talk about something that is very, very important. Everything that we've just talked about is assuming that we are using radians instead of degrees when we measure angles. Now, some of you are going to say radians, what's a radian? But I'm hoping that most of you are going to agree that radians are something that you understand. So tell you what, let's take I want you to type into the chat box. I want you to tell me yes if you have worked with radians before, and type no if you have never even heard of a radian before. And let's find out how many. So I'm seeing a lot of yeses. I'm seeing some people saying yes, but it's been a while. I'm not seeing any no's yet. If you want to send me a private message saying no, that's okay. I won't think badly of you. Okay, so I'm seeing a couple no's, mostly yeses. Okay, so tell you what, let's use the remaining time here to talk about radians. Let's make sure you guys are all good with radians and what they are and why we use them. Okay, so first off, let's talk about why do we need radians? Okay, so if I want to take the cosine of 34 degrees, you all look at that and you say, okay, no problem, can do. What if I were to tell you that I want to take the cosine of 34 seconds? Okay. I'm hoping you're going to look at that and you say, oh, wait a minute, that's not the way it works. You can't take the whatever you put inside of this, the parentheses here, it has to be an angle. It can't be a time. That doesn't make sense. How can you take the cosine of time? That's crazy talk. Well, not if you use radians. If you use radians, it is not crazy talk. So what I'm going to do is I'm going to define a new way of measuring an angle. And hopefully this is review for almost all of you, but I realize not for everybody. What I'm going to do is I'm going to take a circle here. And I'm going to say that the radius of my circle is going to be measured by a piece of blue string or blue yarn. So I'm going to take a piece of blue yarn and I'm going to one end at the center, the other end out here. So that piece of blue yarn is equal to the radius. Now what I'm going to do is I'm going to pick some angle, some arbitrarily angle. So let's say I want to measure this angle right here. This is the angle that maybe it's 110 degrees, except I don't want to measure it in degrees anymore. I want a new way of measuring that angle. Okay, so instead of calling it 110 degrees, I'm just going to call it theta for right now. But I want to define it in a new way. And so here is the way that I'm going to define theta. I'm going to take another piece of yarn, and this time is going to be a red piece of yarn. And I'm going to lay this red piece of yarn along this circle. So the red piece of yarn starts right here, and then it goes up here until it gets to where my angle ends. And then in order to put a number on what my degrees are, I'm going to take my blue yarn and I'm going to put it up here and I'm going to see how many times the blue yarn will fit. So my first one goes about that far right there. Okay, so that's 1 unit in my new way of measuring. Okay, and then my second one here goes up to about right here. And so that's about 2. Okay. So this angle here is going to be approximately 2 units in this new way of measuring it. And so what I'm doing is I'm saying theta is defined as the length of the red yarn divided by the length of the blue yarn, which by definition is the radius. Okay, the length, because this is 2 pieces of blue yarn. That's not one long piece of blue yarn. The length of the blue yarn is fixed. It is equal to the radius. I cannot change that. So it's the length of the red yarn divided by the length of the blue yarn, where the blue yarn is fixed as the length of the radius. Okay, so then what we're going to do is we're going to say this angle then is 2 radians. Okay, so this is a new way of measuring angles. And the neat thing is that it's dimensionless. So if I want to measure the length of the blue yarn the length of the red yarn, if I want to measure the length of the red yarn in meters, okay, and I'm measuring the length of the blue yarn in meters, so my unit on top is meters, my unit on bottom is also meters. Meters cancels meters, so radians works out to be a unitless number. So I could do the same thing in feet. Let's say I don't want to use meters, I want to use feet. Well, as long as I use the same units for my red yarn that I do for the blue yarn, so then I'm going to have feet on top and feet on bottom. Feet are going to cancel out. So this radian is actually a unitless number. So that way I don't need to measure it in degrees. I can measure it in whatever unit I want. I can measure it in seconds. So if I want to do y equals a times the sine of b times t, and I want to put in t as being 29 seconds, I can do that as long as the units of b are in inverse seconds. Okay, so let's say I want my period to be 29. So b equals 2 pi divided by the period. If the period is 29, that means that b then, let's see, what is 2 times pi divided by 29? So my b value then needs to be 0.217, but the units for b are going to be 1/seconds. Okay, so now I can take 29 seconds, and if I multiply it by 0.217, 1/seconds, so seconds cancels out inverse seconds. So what I get is a unitless number, and then it works out. And so I can, as long as I have my calculator set for radians, or as long as I have Desmos set for radians, I can do it this way, and I'll get a graph that makes sense. If I were to measure it in degrees, it wouldn't make sense, because how can that work? So hopefully this helps you understand. This is the reason why we use radians, is because it allows us to stick numbers into the equation that aren't in degrees. We can put numbers in that are units for time. So radians are actually pretty useful. All right, so the bell is going to ring in 1 minute. So I see, so the homework problem, homework problems, plural. Let's go. Okay, here they are. So I want you to do problems 15 through 25. And then I also have posted a special problem in Canvas that is very much like the one that we just did. I want you to come up with the equation that matches the motion of a mass that's going up and down. And I want you to do it basically the way that we just did. Get out Desmos and use Desmos to make sure that your answer is correct. So there you go. Are there any questions before you head out? Okay, ding, ding, ding. I hear the bell ringing. So go ahead and type "bye" into the chat box. And remember, the test corrections are due Saturday at midnight. I'll see you guys later. Khaled, do you have a question? Is that why you stuck around? Here, let me turn off the recording so that we can talk without it being recorded.